Alright, so for this video we're going to talk about integrated integrals, and that's going to be with respect to finding volume of a solid, which will be bounded above by a function of two variables and below by a rectangle. So let's look at that in particular. Let's get our pen in here. All right. So we have z, y, and your x. Let's take a function of f of xy, but just look at the part with the shadow of a rectangle. Some sort of rectangle here. So here's your surface, part of f of xy, and your rectangle down below, which will be between, we'll say A to B here, and then C to D there on the Y. So we want to find the volume of this solid here, right? In order to do so, what we do is we evaluate a double integral, and we can write that just like this. So that's the integral. It's a double integral. You have the integral of f of x with respect to dx from c to d, and then the integral of f of x of what's this value with respect to dy from a to b. So let me explain that a little bit more. In order to integrate the double integral here, it's similar to what you've been doing in single variable calculus, but you'll be integrating one integral at a time. So the inside integral here will be evaluated first, and then the outside integral we'll go ahead and you'll evaluate that. So there's a couple things here. You've got a function that you're integrating here with respect to dx. That means you're going to assume or make y a constant. And then when you do the outside integral, you're making the x a constant. All right. I do want you to go ahead and read 515.1, and you'll read about the Riemann sums. It's a very similar aspect to single variable calculus. What we're really doing is finding the volume of very, very small rectangles or rectangular prisms, and then we're adding those up, summing those up. All right, so let's go to the next slide, and we're going to talk a little bit about how you would evaluate these a little bit more. So the volume theorem gives a practical method for evaluating the double integral by expressing it as an iterated integral, which that's what this is. You've got an integrated integral. You've got two integrals here. I'm going to actually switch to highlighter here. So this is Fubini's theorem, what it really states is that we can take an integrated integral and integrate it with respect to dy first or to dx first. The order doesn't matter. You will get the same answer 99% of the time, because we're going to have functions that are continuous and bounded on R. All right, so this is your rectangle. You're bounded on your rectangle. So that's Fabini's theorem. That gives us another way to evaluate it, the double integral. Now we can also talk about a special case where f of xy can be factored as a product. So here f of xy can be factored as a product of a function of x and a function of y only. So the double integral of f can be written in a particularly simple form. So here we broke down f of xy to g of x and h of y dA. So that dA will be split up into dx and dy. So you can see that the integrating integral can now be evaluated, the integrals can be evaluated separately and then multiplied. Right, so here's your R. R is between AB and CD to make that rectangle. So keeping in mind our Fubini's theorem and theorem 11, essentially, in the book, we have multiple ways to evaluate double integrals. So the next thing I'm going to do is just do one example of this. Let me go ahead and get my ballpoint pen out here. And this example is based off of example, let's go ahead and do example number 4 in 15.4. So this is example 4 in 15.1. At the bottom of the page, 993. I picked this example because I can show Fubini's theorem, but also show theorem 11, and that all works together. So let's just take the integrated integral 0 to 3, and then we've got 1 to 2, and it's a simple one, right? All right. So given as it is, we want to evaluate the integral x squared y with respect to dy from 1 to 2, and then you'll integrate from 0 to 3 with respect to dx. So we can go ahead and do that. Let's do it. Let's do it here separately. So this is a simple integral here, and just to make this video shorter, I'm not going to go through every single step, and you're going to end up with 3/2 x squared. So then you're going to take this and integrate from 0 to 3, 3/2 x squared, and you can look this up in the book for the details of this. And that's going to be with respect to dx now. And then your final answer will be 27/2. Fubini's theorem states that we could take this integrated integral and reverse, right? So we could just go from 1 to 2, 0 to 3, x squared y dx dy. So you see how we've put the dx and the 0 to 3 here in the center, and then we evaluate out. So in this case, right, and again, we're just looking at example 4. We integrate from 0 to 3, x squared, y, dx, right? And we end up with 9y. All right. And then we integrate from 1 to 2, 9y, dy. And again, we get 27 over 2 in the end. What's not continued in this problem in the book is how it can relate to theorem 11. Just a side note here, this Fibonacci's, I like Fibonacci as well, but Fibini's theorem is very similar to Clairaut's theorem. So as you know, you can differentiate, you do your partial differentiation either way, right? So here we go. So this is now I'm going to be using theorem 11. So looking at this one, we've got f of xy being x squared y. We can break this up into two functions. I'm going to break it up into, let's say g of x equals x squared. So it's a function of x, and then h of y. All right, we'll do it that way. Is a function of y, right? So then we can state that f of xy is the multiplication of these two functions. Real simple example here. So using theorem 11, we can integrate separately these two functions. So we take g of x, which is x squared, right? So we're doing that from 0 to 3, x squared, which is our g of x, and then that's going to be respect to dx. And we can go ahead and basically just multiply, right? Multiply by 1 to 2 y dy. Great. And going through this pretty quickly, we get x cubed, right, over 3, 0 to 3, and we're multiplying that times your integration here, which is y squared over 2, 1 to 2, and we get 27 over 3 right there, and we get 3/2 here. Those 3's cancel, right? So in this case, we also get 27 over 2. So here, for these double integrals, we're using Fubini's, not Fibonacci, right? Fubini's theorem. And then over on this right side, we're using theorem 11. So that should give you a good start in giving your ability to integrate these double integrals. Now, keep in mind, ideally, what we're really looking at is the volume, right? The volume under that surface, above that closed rectangle. But you could get a negative volume if it goes below the xy plane. There is no real negative volume, so that doesn't really make sense. But you can think about it that way, or you might have part of the multivariable function above and below, and you might cancel out the two volumes, the negative volume, quote unquote negative volume, and the positive volume, and get 0. Right? In this case, we get the volume of 27 over 2. All right, and that's it.